All right. Yes, so today we definitely want to get to the conversion from NFA into DFA. Before that, we need to understand the behavior of NFA very well. That's something we should do in the very beginning. And I would like to show you guys something, but before that, let's make some introduction. Okay? My favorite quote for explaining the intuition behind NFA, especially how you trace how the NFA processes a string, is the following quote. Let me read it to you so you see if that makes sense. Obviously, the time continuum has been disrupted, creating this new temporal event sequence resulting in this alternate reality. Has any one of you seen this quote somewhere? You guys might be too young, I guess. Huh? No. Way earlier than that. Okay. So this is actually from a very classic movie called Back to the Future. And, but just for your information, I'm talking about this quote in part 2. I'm going to show you a movie clip because that one really is nice. Let me give you some context. The part 1 was released in 1983. I'm pretty sure none of you was born. I'm pretty sure. The second part, which is this quote, comes from 1989. I still remember I went to the movie theater to see this movie. I still remember. Anyway, I was around 6 that time. You guys maybe didn't even exist at that point. Anyway, so before I show you this only 1 minute clip, I want to show you guys. For those of you who didn't watch the movie, if you're interested, watch them series. It's really fun. Anyway, but for this particular part 2, somehow at the abstract level, you can link it to NFA, funny enough. Okay, but let me give you some context. The 1 minute clip I'm going to show to you, you can imagine this will be the context. There will be 2 characters over there. Dr. Brown, who actually is going to explain the situation in this quote, and also the young boy is called Marty. Okay, 2 characters. Basically, let me just give you the context very quickly. What happened was they actually started with 1985, and Dr. Brown invented a time machine in that year. And then they kind of traveled to the future, which is 2015. For us, it's not the future, of course. I'm talking about many years ago. Once they have done whatever they want to do in 2015, they try to go back to their original 1985, but somehow they found that 1985 is no longer the 1985 they recognize. That's kind of the idea we can use to explain NFA somehow at the abstract level. Just for what it is worth, I'm going to show you just 1 minute clip. Okay? I also bring my speaker, so hopefully everybody can hear. All right? Sorry, there's no subtitle here.
The place is boarded up, shut down, so I broke in and borrowed some newspapers.
I don't get it, Chuck. I mean, how can all this be happening?
It's like we're hell or something. No, it's still early, although I can't imagine hell being much worse. Boy, I'm sorry, boy. The lab is an awful mess. Oh, boy. Obviously, the time continuum has been disrupted, creating this new temporal event sequence resulting in this alternate reality.
English, Doc.
Let me illustrate. Imagine that this line represents time. In the present, 1985, the future, and the past. Prior to this point in time, somewhere in the past, the timeline skewed into this tangent, creating an alternate 1985. Alternate to you, me, and Einstein, but reality for everyone else. Recognize this? It's the bag the sports book came in. I know, because the receipt was still inside. I found them in a time machine.
All right. Anyway, it's only part of the story, but if you are interested in finding out the complete series, I'll leave that to you. Anyway, that's about the way I understood NFA, about alternate reality or alternate universe. But let's see exactly how that goes. And of course, I got to show this because I'm going to post this video lecture recording on YouTube, only using this for educational purpose, right? Just make sure my video wouldn't get taken down after today, right? You know, YouTube, they are very sensitive to this kind of thing, but it's only for teaching you guys NFA, nothing else. Okay, anyway. None of you have seen that movie, right? You guys might just be too young. Oh, you have? Oh, okay, good for you, good for you. Oh, I love this trilogy. Part 2 is amazing, just amazing. Okay, anyway, let's talk about NFA. Hopefully we can come back to reality, right? So let's see how the NFA can be understood. All right, so basically, whenever you try to make a transition in DFA, it's deterministic. You know exactly which state you might go to. In the case of NFA, you might need to go to multiple target states, in which case you're branching out to different realities, which I call, okay? Well, so now we need to understand, just using some simple example to see how we can trace the string, because we'll need that intuition to develop the transition function, also formally. I'll give you guys just a little bit of time to think about how it might be developed, and I'll give you the answer, so we wouldn't spend too much time. The main point today is to do the conversion, all right? Okay. Okay, so we don't need this anymore. Let's now try to process this particular string. What we want to know, ultimately, let's say at the top level, we want to know whether or not the NFA over here is going to accept this particular string. That's what we like to know. The idea would be, as long as one of the alternate universes or alternate realities can accept this string, we will be okay. It doesn't need to be that all the universes will need to accept this. We'll see what I mean by that. All right, let's try to do that. Let's start with, let's say initially we start with Q0. Okay. So we start with Q0, and then we're going to read the first character from left to right. After reading 0, according to the diagram, it's non-deterministic, because we can either go to Q0 itself, or we can go to Q1. We got 2 possible realities, right? Either we can go to Q0 itself, or we can branch out over here to Q1. And when we try to read the next input character over here, 0, we have to consider both of them, okay? So now for Q0, we're going to read another 0, in which case, of course, we're going to get either 0 or 1, right? In this case, we're going to get either 0 or we're going to get 1. By taking 0, we're going to get to Q1. By taking, say it again. By taking 0, we're going to go back to Q0. By taking also 0 again. Yeah, should be careful. This one should be 0, and this one should be 0 as well. And that should be Q1. Okay, what about the alternate reality over here? In Q1, can you take 0? Not really, so you get stuck, right? At this point, you reach a dead end for over here. So you can think about, if you follow this alternate reality, you simply get stuck. But that's okay. We still got possible 2 paths for you to try. As long as one of them leads to some accepting states, we're okay. So we haven't lost the hope just yet. So far, we have read 0 and 0. Right, let's now do another one. Let's say we try to read 1. All right. From Q0, if we read 1, we only got one choice, right? Only this way over here. In that way, we're going to go to Q0. What about in Q1? In Q1, we're going to read 1, for example, here. Only one choice. And then 1, we get to Q1. Okay, so far so good? Yes, did I? Go to Q2. Thank you so much. Please do correct me. Sometimes when I do on the fly, easier to make mistake. All right. All right, the next one. Let's finish the last 2 characters. Let's say we read another 0. This 0 over here, for Q0, we know pretty well, is going to go to either Q0 or we're going to go to Q1. And for Q2, can we actually take any 0? We cannot, right? You can see there's nothing defined for 0. That means we'll also get stuck in this reality over here. All right. Final character. Let's use orange. Final one will be 1. From Q0, can we take 1? Indeed, we can. That's fine. If we take 1 from Q0, just go back to Q0. So if you take 1 over here, we go to Q0. That's fine. And then in Q1, if we take 1, we go to Q2. 1, we go to Q2. So we got two final states, one from the first alternate reality, the second one from the second alternate reality. As long as one of them is in accepting states, ultimately, this string will be accepted, right? That's a very simple trace. Maybe that's something how you understood things from before, but it doesn't hurt to brush up. So you can see this one here is accepting states. Accepting states. If none of them is accepting, then the string will be rejected. Any question here? Are we good? This will be one way to trace the string. I'll show you another way, which is also on the slides. Actually, you see both ways on the slide. But this one, I just want to do it completely with you. The second one, I'll just do one step or two. Another way will be a little bit more like a textual, okay? A little bit more formal if you want to write it, more formally. You can think about what's going to happen is this. If you say you want to read the first 0, let me be consistent with the color. The first one should be blue. Let's say initially we're going to be, so we have the delta transition function for NFA. And then for this one here, if we try, initial state is Q0, and we simply read 0. According to the diagram, it's going to give us both Q0 and also Q1. Q0 and also Q1. Right? You can see the resulting state here is non-deterministic. It's actually a set. Since a set can be either empty, means it gets stuck, or it can be multiple states. Right? It's very different from DFA. Let me just do one more, and then you can read the slide to complete the rest. Right? We don't need to waste time doing everything. How do we process the second input over here? According to the diagram, if I want to read the second 0, I need to somehow consider whether 0 will originate from this states or this states. I need to consider both. In the textual form, how do we write it out? Doing this example here will also help when we do the ultimate formulation. How do we express that? Anyone? I'll give you a little hints. Whenever you want to consider how to process this current character, you have to consider what's the result from the reading so far. Right? So here we have read only one character, and the resulting state is either Q0 or Q1. Either one of them can be where the transition will be originated. Right? So let's write it down. It will be either delta, and then we can take Q0 first, and then reading 0. Or it could be delta, and then we take Q1, reading just the same input. And we combine them. What kind of operator do we use here? Do we use the intersection, set difference, or union, right? Which really accumulates. Okay. Okay, very quickly, and then we're done with this exercise. Q0, 0, just Q0, right? Q1, 0. What would be that? What would that be? Q1, 0 is undefined. Not surprising. Empty set. All right? Yeah, I'm pretty sure you guys got it. All right, please exercise to complete the rest. And ultimately, you should be able to get the same conclusion, meaning that the ultimate resulting state will be Q0 and Q2, and one of them is accepting. So that means the string should be accepted. A very typical question I might ask in maybe written test number 2 is to say, given this NFA, show me the step of tracing that string or processing that string. And then at the end, you want to show to me whether or not the string is accepted. Of course, the way you show that it is accepted is by showing that one of the states over here is accepting states. How do you show it is rejected? If none of them is accepting states, of course. Right? So definitely feel free to try. I'll give you just another string to try. Also try 0, 0, 1, 1, 1. That one for sure will be rejected. But why? If you do the exercise, you will see. All right? Guys, any question about this? Yes. Sorry, which one? The text one, this one here, yes. Which part are you? Oh, don't worry, I'm going to make the notes available to you, so just don't worry if you miss something in the class. All right, so that's about the tracing. Let me go back to the slides and see what next. And we'll get to formulation first, and then we'll get to conversion, okay, one by one. Oh, that's the approach number one, okay? Okay, very quickly about NFA. It's a very similar definition as DFA. It's just a way for recognizing or accepting pattern of behavior for token, right? Remember, we're doing lexical analysis. And then it's non-deterministic, and here it's about the non-determinism. The same input label from the given states might lead to multiple distinct states, right? That's why you got alternate realities. Each transition will offer alternative path. You got to consider them in parallel. That might be the complication when you need to handle them. If at least one of the paths will succeed in accepting the string, the whole NFA will accept. If all the alternate paths do not accept that string, then that means you got to reject it. Right? That's the definition. And why do we need NFA? Just at least from the example that we did last time, to check the string ending with 0, 1, it's just slightly easier to actually use NFA to specify rather than DFA. You just got fewer transitions. But we'll see that even though NFA might be more convenient in some problems, in terms of the expressive power, anything you can specify using NFA, you can also do the corresponding DFA, and vice versa. So expressive power-wise, they are equivalent. Okay. And let's do a little bit of formulation, and then we'll go to conversion. Okay. NFA, and we do very similar 5-tuple over here, right? We got states, we got alphabet. These two are pretty easy. And can you guys tell the difference right away? The transition function between DFA and also NFA. Henry, there's P here. What's P? You guys haven't seen this symbol before? Power set. Maybe you guys used to maybe the 2 to the power something, right? I guess. I'm pretty sure you learned about power set before, right? So this is to say, if given a state and an input for transition, the resulting state is going to be a set of states rather than a single one. All right? And remember we talked about total function versus partial function last time. I want to emphasize that point a little bit more. And over the weekend, I'm going to give you guys maybe some additional references if you want to find out more about total function versus partial function. Very few slides to read over. Okay, so I want to just mention very quickly, okay, just about the idea. Okay, so if you recall, in the case of the DFA, okay, we say the delta over there is actually a state given some transition, always is going to be a single state. Okay. So this means, for example, let's say if the sigma is simply 0 and 1. In the case of DFA, if you're in this particular state, let's say S1, okay, and you must make sure you got exactly 2 transitions out, 0 and 1. All the combinations, 0 and 1, and then they will definitely lead to some states over here. Okay, what state it is doesn't matter for the discussion. So that's why in the total function you have to make sure all the combination of the states and also the sigma, in this case 0 and 1, must define some resulting state. All right, that's about DFA. Let's talk about NFA. In the case of NFA, we got two ways to do it. We can say delta here, and then still, and here. Either you can say 2 to the power of q. I think some textbook might show this kind of notation for power set. Maybe that's what you guys learned. I don't know. How did you guys learn about power set? If you remember. Okay. Anyone? Can you recall the notation? Maybe it's not this either. I don't know. That's okay, but at least the one I put on the slides is for power set. So this simply means a set of states. And let's say using a similar idea over here, if I say S1 over here, for example, S1 might say we got 0 here, also we got 0 here, right? 0 and 0, and we might just go to different states. For example, S2, S3. So this will be for NFA. So what we have is, you can think about, in the transition function, one of them would be, we got S1, and then if you take 0 over here, what you will get back is a set of states, S2, S3. This is 1, right? This will be in the delta. Even more important, in the same states, we don't have any definition for the input symbol 1, right? We don't have it. We only got 2 zeros over here. In that case, you can say S1, if you try to take 1, that one there is actually going to give you empty, simply no resulting states, right? Oh, it should be a pair. And this one here is also in the delta. Just trying to give you some examples. So later on, if you want to instantiate the formulation, you will know how to do it. Okay? One more thing to mention. What about the partial function? For the partial function, alternatively, you can say delta over here would be, still, we got Q, we got sigma, but we'll say it does not necessarily have to return a state always. Sometimes it could be undefined. That's what partial function really means. Let me just write it down just to remind you. Partial function means not necessarily every Q and sigma has a defined resulting states. In this case, you can see obviously, if you have S1 over here, and then you try to say 1, and then this will be undefined. For example, for this delta. All right, so you got 2 different flavors to formulate. But for our purpose, we're going to focus on this one over here. It would be much easier, especially when we do the conversion. All right? All right, any questions so far? Are we okay? All right, let's move on. That's good. And we got only one start state, and also we got a set of resulting states, final states, which will be accepting. And difference between DFA and NFA, obviously, one will be a single one. The other one will be a set, which can be empty, in which case that will be undefined. All right? And this is actually what I just showed to you on the previous page, how you can trace the processing of the string. All right? So for this part here, I'll suggest you try that, and then you can compare the answer on the slides. This should be a very easy question to answer in case it appears. Okay? All right. Let's now do very quickly some formulation for NFA. Okay? Let's just try to define that delta hat. Remember we did the delta hat last time. That's something you will review, maybe for written test too. But for delta hat, in the case of NFA, we'll do some very similar pattern when we define that. Let me switch to here, right? And I think this particular example might help us about processing the string. So I'll give you guys some hints to see how we can figure out the formulation. Not very easy, I would say. But it's good to think, at least put some thoughts into it. All right, let's understand the expectation for delta hat first. So it's more like an extended version of the delta. Rather than reading a single symbol, we're going to read a sequence of symbols. That's why you see here, given the states where the transition is going to happen, we're going to read a sequence of characters, input symbols, like a string. And then we're going to go to a set of resulting states. Right? It's a generalized version of the transition function. And we can define that recursively, just like how we did it for DFA. Let's start with something very simple. The base case and also recursive case are the same as before. We got epsilon, empty string, and also we got XA. I will talk about XA in just a moment. What should this be? Let's start with something very simple. I'm now in state Q. I'm reading, or I have processed empty string. You want to be very precise here. I can tell you that simply say that's Q. Oh, sorry, simply saying that's Q here is not right. Yes? Hmm?
Like it could be any other state.
It can be any, oh no, remember we are now in Q, right? And we are reading only epsilon. What should be the resulting states? You're saying it can be any other states?
Yeah, so P of Q.
Oh, you mean just Q? Not really. Not really, because remember we're talking about NFA. We don't talk about any epsilon transition. We don't have that. We'll talk about epsilon-NFA after this. For now, we assume there's no epsilon transition. Q in a set, yeah. Maybe you meant a singleton set, right? Good, very good. Okay. That's exactly right. So the main point is you cannot just say Q. That'll be the case for DFA, all right? A singleton set. This one is going to be lots of fun. Okay. Okay, for this one here, how about this? I'll give you guys a little bit of hints from the example and see how close you guys can be. I don't want to push you too much, and then I'll show you the final answer, right? Thinking this way. If you look at the pattern over here, we're saying that A here is a single input symbol. And the pink one I'm going to write over here, X over here is actually some prefix. So I'm following the same convention as before when we talk about formulating the DFA, delta hat. So you can think about X, what can X be? Let's say the X is about after reading 0, 0, 1. Let's say, for example. Oh, actually, you know what? How about this? It's after reading 0, 0, 1, 0. It could be. Let's say that's X. And then what about A? A here, let's say, is simply the last character to read to complete processing the string. This will be A. Okay? And now we want to somehow use this pattern over here to define what should appear on the right-hand side. Okay? I'll write down some example relationship over here, and you guys can see how you can generalize it to see how much we can go. So what we have is something like this. I'll put it here. If I say delta hat over here, let's say I start with the initial state, Q0. Okay? And then I'm trying to process the entire string. Okay? Let me just change that to B. I want to be consistent on the color. Okay? The entire string to process will be 0, 0, 1, 0, 1. 0, 0, 1, 0, 1. And we're going to break it down into two parts. The first part will be just the last character. The second part will be over here, the prefix. All right, so far so good? We can do something very similar to what William actually suggested last time, but I'll just write it down directly. This one here can just be, let's figure out what the state would be after reading Q0 and then 0, 0, 1, 0. 0, 0, 1, 0, which is the prefix. And then we want to see what's going to be the resulting states. From there, we can say delta. Whatever the resulting state is, and then we can put delta of the resulting states. Let me just put it in the right place. It's not exactly right, but to see how much you can. So this will be 1. Something like that. Let me say it again. We are saying starting from Q0, we're reading 0, 0, 1, 0. That should give us something. Based on that, we're going to read the last character using delta, because delta would be suitable for just a single state, right? But this is not exactly right, I can tell you. Why is this not exactly right? First of all, this guy over here is not a single state, because according to delta hat, it will return a set of states. That's number one. We're getting somewhere, but not exactly right. This guy over here is actually a set of states. So somehow you have to go to each individual member state in that set and then apply delta. But delta itself is also going to give you a set of states. That's where the complication comes from. Okay? Brilliant. Are you getting something?
Yeah.
You have something. Okay. No, I'm not. Guys, I just want to, okay, up to this point, I just want to show to you, you cannot just apply what you used to have for DFA formulation directly because of the complication we got. So I'm going to show you just the final answer right now. And William can just confirm. All right? Unless you want to share what you have. Okay. Let's just see this. All right. This guy over here. I'll make it a little bit larger here. Okay. What does that mean? I'll try to visualize that a little bit for you, to help you. This is to say, if I want to go from Q here, and then I need to read X first, the prefix. Let's say this one here is going to be any Q prime will be the prefix. Okay. Q prime over here will be the resulting states after processing X. You can see here we're doing delta hat QX, which is similar to what I did over here. Right? But it's going to be a set. So we're going to say every such state from that particular set. From there, we're going to make one more transition. To make that one more transition over here, if you see here, delta Q prime A. This one here is also going to return to you a set for each one of them. So now, how do you union individual sets into a bigger set? You need something called the generalized union. Okay? Let me give you just one more example, right? And then I think you guys should really dive into this definition a little bit more. Okay? Just do one more. So how do we write this one properly? Okay? Let me write it down here. It would be something like this. So Q0, 0, 0, 1, 0, 1, right? Just don't forget, this will be the prefix. It's actually going to be a union of two parts over here. Because we know, after reading 0, 0, 1, 0, according to that, we got Q0, Q1, right? That will be the resulting state. So what can Q prime be? Q prime can either be Q0 or Q1. Q prime over here could be either Q0 or Q1. It can be. And then from either Q0 or Q1, we can make the final transition over here. So it's going to be delta. Let me just remove the lines over here. Think about here. So we can say delta, and then we have Q0, and then we take the final one. And also delta, it could be Q1, and then we take the final one. And what's this one here? Q01. Q01, let me double check. Q01 is going to be just Q0. It's going to be Q0. And what about Q11? Q11 will just give you Q2. Q2. And if you union these two together, of course, you will get the answer, Q0, Q2. All right? That's just an example to understand. Okay? Are we okay with this? Could be a little bit dry, could be a little bit confusing, but you would just need to work out the example, okay, to see the definition. Any part you want more clarification? Any part? Okay, or you can ask me later if you want to. All right. One more diagram for what it's worth. We start with Q. All right. Think about we start with Q. after taking some processing x, we get to any of the intermediate state q prime, not a single state. And then from q prime, we're going to make one more transition by taking a over here. After that, that would be the kind of the step we want to work out. And this guy here is exactly this guy here we're expressing. But we need to use a generalized union. All right? Okay, so that's about the most complicated part, I would say, for today, for formulation. Right? You just need to put so many things together. All right? Okay, if no question, I believe we're getting very close to conversion, and we'll do it together. Okay, and this definition, I'm not going to bother you. This one here, just to say the resulting states must contain at least one that's actually accepting. So that's why the intersection with the final states is not empty. All right, so that one there should not be surprising. I'll just reveal that so you will see that when you get the notes. That one there, we don't need to pause. Okay. Okay, now we can get a conversion. Before that, let's just see very quickly some context. NFA could be very convenient for some modeling scenario to specify certain solution for some problems, but expressive power-wise is the same as DFA. And so here, okay, just about non-determinism. That one just repeating. Okay, in practice, okay. One good thing about NFA is typically, if you for many problems, if you specify that in NFA, you will tend to get fewer states than DFA. As we'll see in the conversion, in the algorithm, we'll see that given arbitrary NFA, in theory, you can get up to 2 to the power of that many states for the corresponding DFA, exponential. Meaning that if you specify something very simple in the NFA, the corresponding DFA could be much larger. So that means, why don't you specify in the NFA in the first place, and then maybe do some compiler to actually transform from the NFA into DFA, which is what you guys do in assignment number 1. That's kind of the insight. Okay? So in practice, you may just want to do it in NFA, or even epsilon-NFA, and then convert that into DFA automatically. Yeah, so that's something we would like to see why. That's something I also want to show to you. Right? That's also very important. Why 2 to the n? Okay, all right. So now here's something very quickly to check with you guys. Okay, a language accepted by some NFA is accepted by some DFA. Anything you well, basically, if you got an NFA, you can always find a corresponding DFA. Right? To express that formally, you would say, for every n such that n is an NFA, it would be the case that there's at least one corresponding DFA such that their languages are the same. And my quick question for you, what about vice versa? Let's say given some DFA, is it always possible to find a corresponding NFA that will accept the same language? Not quite, but thank you for sharing. But actually, you may want to think about, let's say, given some arbitrary DFA, is it possible to find easily the corresponding NFA, which will accept the same language? That's basically what you want to think about. Mm-hmm. Anybody? Other than Henry. William?
Yeah, I'm pretty sure every DFA is also NFA.
Aha, that's exactly what I'm looking for. Okay, so guys, it's a very important observation which we haven't really said, but maybe that's obvious already to you. Let me write it down explicitly. Basically, what we are saying now is every DFA is an NFA automatically. It's just a special case of the NFA where you got the transition defined for every input alphabet. Special case. On the other hand, not necessarily every NFA is a DFA. That one there, how do you find a counterexample? Well, basically, NFA, if that one there, if the NFA, for example, has some missing transition from alphabet, missing transition, which means it's only a proper subset of the sigma. In that case, it wouldn't be a proper DFA, right? That's why it's not necessarily the case. Are we okay with these two statements here? Hopefully everybody is comfortable, right? So that's why when I said vice versa over here, it would be yes, trivially, because given some DFA itself is the NFA that will accept the same language, right? That's why. Good. And before we start the conversion, any question so far? Are we good? Any clarification you might need before we go on? Good. Okay, let's do conversion. We don't assume 2001, of course. But if I was to teach you guys in 2001, I may not show the so-called lazy evaluation to begin with. What we typically do is to figure out what would be all the possible state combination from the NFA and try to see the reachability graph from there. But since now we are more like a reviewing and crash course on the basics, so we wouldn't go that way. That one's okay. Let's go directly to the so-called lazy evaluation mechanism. That one there can also be implemented using some pseudocode, which I'll show you as well. You might find it useful, maybe for your assignment number 1. Okay, lazy evaluation. So has any one of you seen this before? Lazy evaluation in your 2001? If you haven't, that's good. Let's now learn that, right? Or maybe you just forgot. Let's do it together. So now the goal would be, given some arbitrary NFA, we would like to convert that into its corresponding DFA. Let's now just double check, first of all. This is not a DFA. Agree? Can anybody tell me why it's not a DFA? Where can I see the violation? Yes, go ahead. Q0. Because, be more precise. Yeah, because 0 here can go to either Q0 or Q1. Okay? Any other violation?
Not every state Q1 has no 0.
Yeah, exactly. Like Q1 here has no 0, and also Q2 here has no 0, 1. Exactly. Good. Okay, so we definitely got some work to do. We want to convert this NFA into some valid DFA. The technique we're going to do is called subset construction. Sounds like a fancy name, but basically we're just constructing the so-called reachability graph, which I'll show you the algorithm after we do the example. What we want to do is we want to somehow produce a transition table over here. And that transition table is going to be used to visualize the corresponding DFA. All right, so let's try together. I'll show you the steps. Okay, that's the first one. Okay, the same NFA. We know that. Let me just try with the first row together with you, and I'll give you some hints about doing second one, and I should let you guys try. Okay. We'll start with Q0. And this is something called a subset states, meaning that each states in the DFA that we're going to produce corresponds to a set of states in the NFA. Or more precisely, it's a subset of the Q. Right? Remember, the Q is all the states in the NFA, but it's going to be a subset. Okay, that's something I want to mention. Subset state is a very special term when we do this subset construction, subset state. Let's see. Because the initial state is simply just Q0, so we want to put Q0. So notice how I put it, Q0. We'll start with this. The goal will be, we want to see what will be all the reachable states from Q0. As soon as we don't find any new reachable states, we can stop. In the worst case, you may just have to consider all the subsets of the states from the NFA, which would be exponential. All right, let's see. In this case, don't worry, it's not exponential. Otherwise, I wouldn't choose it to do in the class. All right, it's rather pleasant to construct. Let's try. The idea will be very simple. You basically want to see for every state in this particular, well, let me be very precise. For every state in the subset state, you want to see how reachable they are. In this case, we got only one single state to consider. So what we'll do is we're going to get delta over here, and from Q0, we might take 0. Also delta from Q0, we might take 1. Right? And then in this case, Q0, if you take 0, is going to be Q0, Q1, right? And for this one, if you in Q0, if you take 1, it's going to be just 1. Right? Just double check, just in case I did it wrong. Q0. And you can think about this is the initial subset state. And from here, we identified 2 new subset states reachable from there. The first one, actually only one new. This one here is actually new. This one is repeating. That's the first row. Are we okay with this? Anything that's confusing to you for the first row? Let's do the second row together. I'll let you try the following. Okay, the second one. How do we go from here? Let's now draw a line over here. Basically, this one has already been discovered. So I would say already discovered. I'm using a term which you will see in the later pseudocode. Discover already. So this will be the only one that we have to proceed further. But from here, we might see some new reachable subset state. So we're going to put Q0 and Q1 over here. All right, that's what we're going to do. I'm going to do 1. All right. Can you guys take a guess? What should we do in these 2 columns? For example, here, we want to find out in this particular subset states, which basically contains Q0 and Q1 in the original NFA. We want to see what would be the reachable state from either Q1 and Q0 altogether. So what should we do here? What should we do? Yeah.
Delta of Q0, 0.
Let me do it right away. Delta Q0.
0.
Thank you. And then?
Union delta of Q1.
Absolutely. Right? You can see we are basically trying out Q0 and Q1. And also, since now we are talking about 0, so that's why it's 0 over here. All right? And that one there is going to be Q0 will be, let's see, Q0, so Q0, Q1. And then Q1, 0 will be empty, right? So the union has no effects. And you can see this guy over here has been discovered already. So we don't need to proceed any further from this particular one. All right, your exercise. What should be this? What should this be? Okay. Why don't you guys compute and then let me know the answer. What should this be? To start with, it shouldn't be surprising to you, right? It should be a union, either from Q0 or from Q1, right? It could be from Q0, and since now we're talking about 1, so that'll be 1. Union, delta, Q1, and then 1. Right? Q0, Q1 corresponding to Q0, Q1 here in the subset state. 1 and 1 here corresponding to the column. Right? Just make sure you don't get lost. And what should be the answer? Anybody want to tell me the answer? Mm-hmm. Just Q0? Let's try to check. Are you sure? Q0, Q2, you're missing one. Do you see why? Okay, Q01 over here will give you Q0. That one's good. But Q11 is going to give you Q2. You're missing that one. Yeah, exactly. Just be careful, of course. Okay, Q2 over here. And apparently you can see the Q0, Q2 is a new subset state to consider further. All right? And I think you guys kind of get an idea. So what I will do is I'm going to just put it over here, Q0, and also Q2, right? This will be the new starting point over here. You got to keep going, okay? And of course, that would be something you should really try to complete yourself. I can tell you that back in winter 2020, when I gave them the quiz, I basically gave them just one NFA, and then use the lazy evaluation to convert the corresponding DFA. And of course, if you use the lazy evaluation mechanism, you don't necessarily know how many rows you will need. In theory, you might need 2 to the power of how many states there are in the NFA. But I wouldn't give you that in the quiz, don't worry. Right? So, but there might be several rows you have to compute. All right, exercise for you. Meanwhile, let's just see very quickly. In this case, we're lucky. We just got one more, then we're done. So how many states do we have in total in the corresponding DFA? 3. All right. This will be the state number 1. This will be state number 2. This will be state number 3. Okay. And now the question is, how do you draw the corresponding DFA based on that? Right? Let's just do very quickly, right? Just in case you guys are not really sure. We got 3 states over here, 1, 2, and 3. So you're going to put Q0 as 1 state over here, and also Q0, Q1, the second state, right? Just look at how many rows you actually got. And the third one will be Q0 and Q2. Right? And of course, this will be the initial states. That's where we started. Initial states. Okay? By taking 0, we should go to Q0, Q1, which will be here. And by taking 1, we'll go to Q0 itself. Right? This will be 1. And that will be 0. 0 and 1. Right? And etc. That's what you got to do. Why don't we finish that? From Q0, Q1, taking 0, it will be itself. And then if you take 1, it's going to be Q0, Q2. And then finally, Q0, Q2. And then here, if you take 0, Q0, Q1. And take 1, you get Q0. Does that seem familiar to you? That's something we did earlier, not long ago. Let me just show to you. You can look at the slide as well later. That's what we did last time. Exactly this guy here. It happened to be. Not necessarily to be the case. All right? All right. That's about how you can do conversion here. I can maybe give you guys maybe some example, maybe over the weekend, maybe next time. You can definitely give it a try. If you want to show me your answer, feel free. All right, I'll try to give you some. And the next part is to go over the pseudocode. But before that, why don't we let you guys take a short break by taking attendance? Why don't we do that? Okay. Oh, somebody walk out, right? I'm pretty sure he's coming back, right? Yeah. Okay. Let's take attendance first. Yeah. Yeah. Too bad. But that's okay. I'll make sure I'll count him. Yeah. Yeah. Bear with me. I just need to refresh the location. But I promise Monday we'll finish the scanner thing. We'll move to parsing. I promise. Sorry, not Monday, Tuesday. Keep getting confused. Monday is for my 2030 class. Okay, so if I say start a class right now, and let's see. Give me a moment. Are you guys able to see the poll? Okay, yeah, just before he comes back. So let's do that. Yeah, he better come back, I hope. Yeah, any trouble you guys ran into? Everybody's okay? All right, awesome. Yeah. Can you join?
Yeah,
It's
it's not connected.
not connected? Come over. Yeah, otherwise, guys, I would suggest, let's see, right now it is 2:28. Let's take a 3 minutes break, okay? And then we'll resume. Yeah, can you actually join?
Yeah. This one.
Hang tight. We're checking you into the class. How about you? No? Okay, let's make it easy. Okay. Can I borrow some sketch paper from you guys, if you don't mind? Thank you. Just one. That's okay. Don't worry about it. That's good enough. Yeah. Can you use your pen? Just temporarily. Thank you. Oh, sure. Thank you. Thanks so much. Yeah, guys, let's do this. But we're gonna make sure it's actually sorted maybe next time. Can you please just put your last name, first name, student number, and signature? That'll be good. Thank you. Yeah, you as well. Yeah.
Okay, cool.
Oh.
I am in, but it's not like.
Yeah, this weekend we. Oh, could you put your name? That's okay. Yeah. Yeah, please put it legibly so I can read.
Oh wait, I opened the app again. Where it works now.
Good, good. Yeah,
just,
awesome. Good man. Hello, iClicker, please. Okay, thank you. When you're done, let me know so I can close it. Done? Thank you. Yeah, let's wait for 1 more minute or 2.
Yeah. I don't.
Then you can look at my GitHub. To exchange with the GitHub or all of the Textual assignments. A lot of to show people.
No, it has one of the things like forks of hooks for Windows 10 calculator. So you can execute like code on the calculator and have it run without being active kind of thing. Like that. Just fun stuff.
Lots of forks.
Yeah, just forks.
All right. Why don't we get started again? Okay. Quick question. So we got assignment 1 due, right, on Monday. Okay. So are you guys okay with it? Do you assignment? Since we only we kind of expect you to submit your best effort. So in that way, I wouldn't mind extending it for a few more days if you guys really want to, polish that, make it more perfect. Do you think that might help? Okay, why don't we do that? Okay, okay, good. Okay, yeah. But assignments, I'm very flexible. But for project, please, for project, you gotta really make sure stick with the schedule, okay? Why don't we say this, okay? I can tell you why. Reading week, you're really supposed to get very busy with the Untitled 4 tutorial. Your project depends on that. Your assignment depends on that, and also your programming test depends on that, right? Okay, how about we make it Friday? Okay, I'm gonna confirm. So let's say Friday, 2 p.m. All right, done. Unless I got any objection. No? Objection? No? Okay, very good. Right. All right, let's now come back. Okay, so this one here, just a pseudocode, which is on your slides. I'm not going to trouble you too much by tracing line by line. I'm pretty sure you'll get lost very easily. I mean, for this kind of code, you just have to go very patiently to trace some example, just one, then you'll get it. And this pseudocode notation, we will see many more when we get to the parsing part of this course. We'll get top-down parsing and bottom-up parsing in the pseudocode notation. I think we'll spend more time when we get there. For this one here, I want to highlight something for you very quickly. Okay? When you study this particular algorithm over here, right, I'm not going to trace everything, but I just want to highlight something for you. Number one, you want to notice what the variables are in the pseudocode. So we got something called reachable, and we got something called to discover. And also we got something called not yet discovered. So these are the three main variables you want to pay attention to in the algorithm. Okay? So for the reachable, basically, it will be all the set of states we have accumulated so far. For example, you can see this is one member of the reachable states. This will be the second member. This will be the third member of the reachable. Eventually, you want to accumulate it as many as necessary. That's why it's called lazy evaluation. And to discover over here is, out of all those reachable states, which one to actually look at next. For example, let's say this. Initially, we got Q0 to be the reachable, the only reachable state. We discover this one here and this one here. What will be the next one to discover? We definitely don't need this one here because that one has been discovered already. It will be this one, right? So somehow, this particular equation over here will help you decide what will be the not yet discovered. So I would say you guys will pay more attention to this particular expression over here. If you got trouble understanding it, reach out to me, all right? This part over here is to determine whether or not the lazy evaluation should really continue, okay? To determine if the lazy evaluation should continue. Right. Other than that, I think everything you see over here corresponds to exactly how we did things before. So there shouldn't be any tricky things. But you want to make sure you're really convinced the algorithm was actually correct. All right? Excuse me. Let me just go over some very quick facts about the algorithm. And then we can go on to epsilon-NFA. Okay, let's see. Oh, by the way, so here there's a little line over here to say you can compare the converted DFA versus the DFA we specify in the first place. They happen to be the same. All right, so just to, in some way, it proves actually it works. Okay, there's pseudocode over here, and then what I want to show to you. Okay, this will be something I want you to try to answer to yourself. What will be the running time for the reachable subset states over here? Reachable subset state, that's the algorithm. What should be the running time? I'll give you a little bit hints, okay? When you think about this question here, because the running time is going to be dominated by this while loop. Specifically, it's going to be dominated by how many iterations the while loop is going to do. Specifically, how large, how many iterations it will take for the to discover to become empty, meaning that nothing more to discover. Yes? Yes, that's actually right, exponential, exactly. Because we talk, why, Henry, can you elaborate on that? Why would that be 2 to the n? Yes, in the NFA. Yeah.
In our DFA, our states are essentially composed of some combination of our NFA states.
Yeah.
Specifically, everything either our composed state can either have or not have every given state.
Yes.
So the number of possible DFA states is 2 to the n.
Mm-hmm.
And our while loop has to go through
Yes, yes, that's correct. Basically, given a set of states, you want to find out the number of subsets in that set of states. But I want to just do one more thing, just in case some of you might still have trouble. Let's say in the NFA, just for example, you have S0, S1, and also S2. In the worst case for DFA, according to Henry, it's going to be 2 to the power of 3, right? 2 to the power of the Q. In this case, Q will be 1, 2, and 3. That'll be 8. What does that mean? In the worst case, you might find that you might need one DFA state which will correspond to empty in the NFA. You might need one state which will correspond to just S0 in there. You might have another one which will correspond to maybe S0, S1. You might have another one corresponding to S1, S2, and etc. And finally, you might have another one correspond to S0, S1, S2. So I think usually maybe in 2001, in case you guys took it, they might kind of show you this kind of the most like a inefficient way of calculating it, which can be 2 to the n. But for lazy evaluation, the worst case, you still have to reach 2 to the n. But in practice, you wouldn't have to go that far. All right. And pseudocode, I'll leave that to you. I promise I will focus more on the parsing algorithm, which might be new to most of you, so we can spend more time on that. All right, 2 to the n, and then, yeah, lazy evaluation will be efficient in practice. All right. Epsilon-NFA. So today, for the rest of the day, let's do some example, sketch, and then we'll do just one specific calculation which will be important for us to convert epsilon-NFA into DFA. That's something called epsilon closure. Let's do that. Hopefully we can do that. And then on Tuesday, we can finish the conversion and do 2 more things, and we are done. And then, well, not for the course, but to the parsing. All right, so let's now try number 1 here. Look at this language description, which you guys are pretty good in reading, I hope, right, after preparing for quiz number 1. Now the challenge would be, you don't need to draw that on paper. Maybe think in your head. We're talking about NFA, no epsilon. All right? How would you draw the NFA for this? I'll make your life easier. I'll make in the following way. You can assume you might have some diagram over here, like this cloud over here, that NFA would solve this problem. You might just have another NFA over here that would solve this problem over here. Is it useful? If I give you these 2 NFA individually, is it easy for you to simply combine them so that the resulting NFA could be the NFA you want for the entire language? Basically, I'm asking, given solution to sub-problems, are you able to compose the sub-solutions to the ultimate solution? That's basically what I'm asking. Is it possible? If it is not possible, then it sounds like it's quite difficult to specify this in NFA without some extra help, right? You guys can think about it. This might be maybe a similar, maybe motivating example you were given when you first learn. But if not, that's okay. Now this will be the motivating example for you. If you do believe it's very easy to specify that, you can also say that. That's okay. Before we take any potential answer, if no, that's okay. I can tell you what the answer should be. Can someone at least tell me informally what this language would be? At least. Can somebody try? What's that language? Henry?
It has usually has a 1 0 1 0 1 0. Always has a 1.
It's only 0s and 1. That's for sure. Yes, but what will be the pattern for that for each member in the language? Mm-hmm. Yeah, anyone else? If you want to also contribute, you can also feel free. Well, if I look at that, it seems to me every member string in the set can be broken down into two parts, right? The first part, X, is going to satisfy this pattern rule. The second part is going to satisfy this pattern rule. That's how I would put it informally. You did? Okay. Sure. All right, so let's say given this, how can we, let's say I already got an NFA for specifying this, which we did earlier. I also got another NFA, which will recognize this pattern over here, which we also did earlier. Is it possible to combine them directly without too much more work? You found a way to do it? Yes, go ahead.
All right. So, roughly speaking, first NFA, and you find all the accepting states, and then you make those the initial states of your second NFA, and you just copy that second NFA into all of them, and then you just have this giant arithmetic.
Okay, I see what you mean. Basically, yeah, I see what you mean.
Yeah.
Basically, what you're saying is, yeah, actually, that's interesting. Okay, that one basically is about epsilon-NFA idea. Epsilon-NFA will just make it easier to do the copy and paste. Okay, well, guys, in case you kind of follow what William's saying, which is brilliant, that's good. In case no, let me tell you what's going to happen here. Okay, what's going to happen? Let me just sketch the idea. What William says is completely right. Let's say we got some initial states for this NFA, right? The first one. I'm not going to draw the complete picture. Okay. There might be several accepting states, for example, over here, let's say 2. There is another maybe starting states in the second NFA. What we do is, what you said, we simply maybe make one copy and put it here. We make another copy and put it here. Okay, that's awesome. I think that will work. But epsilon-NFA make it easier for you. What you can do is, you can simply say, change this into a normal states. Change this to a normal states. And then connect them using epsilon. That's the essence of understanding what epsilon-NFA can do for you. You can sometimes move from state to state without any effort. But this is actually very abstract. To really make it implementable, we will need to convert that into DFA, which we'll talk about for sure on Tuesday. But I want to go just a little bit more about epsilon-NFA before we let you go. I'll go only 5 minutes more. All right, similarly, I think I'll try to bring the corresponding epsilon-NFA to show to you on Tuesday. I didn't prepare that. But for this one, it will be similar idea. Okay? Let's say, for example, this one here, we can go for either this way, or we can go this way, over here, right? Let me call this maybe 1. Let me call this number 2. I'm pretty sure you know how to draw 1 and 2 separately, right? These are pretty straightforward. If I got some NFA over here, NFA 1, which will recognize 1. I got also NFA 2. They might have certain accepting states. Keep them, don't move them. Okay, don't move anything. What we can do, so they definitely have some initial states. So now in this case, what do we do? We basically say, create a new initial state over here. This one here can either go this way by epsilon, or it can go this way by epsilon. That's it. So epsilon-NFA at least are very convenient for solving either you're finding this kind of a concatenation problem or like a union of the property problem. If I change this one to be in conjunction, it's another story. It's not that easy anymore, right? But at least for these two. So I would suggest, I'm going to do a little bit more. before I let you go, but what you want to really try is to see how you can create the corresponding epsilon-NFA for these two. So these are the very two typical problems that epsilon-NFA can solve pretty well. Let me see if there's anything else. Okay, this is just another one. And this will be the complete solution for this particular one. Right? You can take a look. I'll let you study that yourself. And then we're going to formulate the epsilon-NFA. We only got 3 minutes. I would say I stop here. And then on Tuesday, for sure, I'm going to finish the formulation. I'm going to talk about how we can convert epsilon-NFA to DFA. And then we got one more from epsilon-NFA into regular expression. And then minimizing DFA. We'll do all of them. We'll finish that on Tuesday. Before the reading week, we'll move on to parsing. All right, guys, take care, and then I'll see you next Tuesday.